So the last topic we want to cover under momentum methods is impact. Now, it's kind of tightly related to the concept of linear impulse and momentum, and you'll see that. Now, impact, it's actually an important topic in engineering mechanics. We can go way deeper into this topic, and there is a lot to discuss, but we're just going to stay uh, within the scope of discourse. All right. So, generally speaking, impacts happen in many situations in engineering systems, right? Think about machines that are performing, let's say, some kind of stamping or forging operations in some manufacturing environment, right? There is an impact there. And when you do when you're stamping something, or you are doing some, even let's say, some kind of forging operation, as I said, there's an impact between the tool or the machine and whatever material you're trying to stamp or do the forging operation on. Uh, Vehicles, right? Vehicles that impact each other intentionally or unintentionally, like railroad cars when they hit each other during the motion. You know, you think about the subway, a train, a subway, or subway cars, right? There is an impact between them when the whole train starts moving, or there is some kind of braking, or when there are or in car accidents, right? It's either intentional or intentionally or unintentionally. Unintentionally would be obviously the accidents happen uh, probably every day, everywhere. Not probably, definitely everywhere. Like cars get into accidents, or intentionally would be when they are doing some kind of safety evaluation for different types of cars. Let's say there is this specific kind of car manufactured this year by some manufacturing company, and the some agencies trying to rate this car in terms of different types of safety or different environment that the car can be during an accident, and they want to give it some kind of rating. So that would be an intentional situation that they simulate this car accident. So that's also another situation you will see impact, and we study actually the impact in those situations. So, but the general question that we're trying to answer, at least in this course, when we talk about impact, is that we know the velocities of two objects, right? In a car accident, we can think about the velocities of two cars that are about to have an accident. We know the velocities of two objects, right? Before they collide. Hmm. Now we want to determine their velocities afterwards, right? That's the whole idea. And we want to know what is the effect of impact on the motion of these objects, right? So we want to, again, we know the velocity before accident, immediately before accident, typically that's how we phrase it. We want to know what is the velocity after the accident, and also we want to know what is the effect of impact on motions, impacts on the motions of these objects, right? So let me put it under impact. So impact, and let's write it this way: impact happen in many um, situations of interest in engineering. Right? Example would be uh, such as machines performing some kind of stamping or forging uh, operation operations, vehicles that impact each other intentionally or unintentionally, right? Like let's say railroad, cars, or cars in accidents. So it does happen, right? I told you the general idea that we just want to study the effect of impact on the motion, right? This is dynamics. We are studying the motion of objects, right? Objects in motion. We want to know what happens. How can we analyze it? We want to be able to predict what happens next if you're in a specific let's say a specific moment during the motion. We want to have that capability to predict what happens next, and we want to study the analyze of different types of motion. One of them would be the impact. We want to know how does that affect the motions of objects, right, involved in this impact. So how do we do that? We are actually going to study the impact using linear impulse and momentum. Right? So we kind of we covered linear impulse and momentum. Remember before previous class and class before that we were talking principle of angular impulse and momentum. But before that we were talking about principle of linear impulse and momentum. And now we're going to use that to study impact. Right? In a simplest form, you can think about two objects moving towards each other. There is an impact, they collide, and then we want to use linear impulse and momentum to study what happens. And as I said, we want to know, if we know the velocities immediately before impact, what would be the velocities of these objects after this impact, which as a result, we can actually get information about the motion of these objects. I'm going to put it under conservation of linear momentum and impact. And the reason we say conservation, because what we do is that we are going to say, well, let's assume that when this impact happens, there is no other external force. So no energy is added to a system. Whatever energy is in the system is conserved, right, before and after. That's the main assumption we make. So no external force is applied aside from the whole impact phenomenon. And even if some external force is applied, since impact is happening in a very short period of time, the force that is applied to the system, external force, in that short period of time can be neglected. It's very small compared to the force that we have during an impact. Think about a car hitting a wall or hitting another car. A lot of force, a large force involved in this accident, right? So if there is, I don't know, if there is some friction between the tire and the road, right, in a fraction of a second, that amount of force in that fraction of a second is really, you can neglect that compared to the huge amount of force involved in this accident because of the impact between these two cars. So I'll put it under conservation of linear momentum and impacts. Right? So consider two objects, object A and object B. They're going to be in an impact. They're going to collide. If there is no external force that affecting the system, or that external force is very negligible in that short period of time that this impact happens, we can say that the linear momentum of the objects is conserved. Right? So no energy is added to the system, no energy is extracted from the system by any external mechanism. Right? Impact before and after. So we only are focused on the impact. So let's think about it this way. We have some object A, I did a pretty bad job. I didn't identify that as a circle. Right. So let's try it again. No, don't give up on me yet. I'm going to try it for a third time. If it doesn't work, I'll just go with my ugly shaped circle. All right, so this is one, let's say object A, and then we have object B. All right, so let's call them properly. This is A, this is B, and then they are moving towards each other. So this is going this way, this is going this way. This is before impact. Let me see if I can draw it in a better way. This is before impact. I don't know if I made it better. So this is going this way, it's going this way. And then they reach, they collide, the impact happens, and then we'll see what happens, right? So let's write it this way. Consider object A and object B, right, in an impact if there is no external force that, let's put it this way, or the effect of external force can be negligible, right? As I said, could be small compared to the large force that basically is applied by one object on the other and the other way around. If that external force is very small compared to that, we can basically neglect that. Force can be negligible. Then we can say the total linear momentum of the objects is conserved. Right. I think that it's the same before and after. Let's think about it this way. Now, when there is an impact with no external force, right? There is assuming no external force. Whatever force object A applies to object B is the same amount that object B applies to object A, right? This is Newton's third law, simply. So if you say, I can put it this way, FAB is equal to FBA, and FAB is the force, let me write it this way, is the force exerted on A by B, and you can think about FBA, the force exerted on B by A. And they are equal, right? They are the same. Now, let's apply principle of impulse and momentum for each object. All right, let's do that and see where does that take us. Remember, principle of impulse, linear impulse and momentum. We said the integral of force, resultant force, there was only one force on each object. dt, right, that was the time integral of force in some time period from t1 to t2 was equal to change in linear momentum, mv, right, mv2 minus mv1. So here's what I do. Let's say Principle applying the principle of linear impulse and momentum to each object, don't say during the impact, to each object. So for object A, I'll have integral from T1 to T2 FAB dt. Force A is applying to B. So if you draw the free body diagram of A, it's just A, and the FAB, the force A is applying to B, or B is applying to A. You can actually switch, they are the same, is equal to M A VA, and here I use prime. Don't get confused with this prime. I'm following your textbook's notation. Prime is not derivative here. Prime means velocity at T2, right? Minus MA VA. So this is velocity at T2. This is velocity at T1. Velocity after, velocity before. And we can write this for the other object from T1 to T2 F BA dt is equal to M B V B prime minus MB VB. Same story. VB prime is velocity at T2 for object B, and VB is velocity at T1 for object B, right? So that prime represents the velocity after. Now, in this expression, in these two expressions, if you look at these two equations, well, we established already that the left sides are equal. This is equal to this one, right? If the left sides are equal, the right sides should be equal too, right? Hopefully it makes sense. That means since the left sides are equal, then right sides are equal. So that becomes MAVA prime minus, let me write it in a better way, MA VA prime minus MA VA is equal to MB VB prime minus MB VB, right? Or we can just move things around and also write it this way, MA VA prime plus MB VB prime is equal to MA VA plus MB VB. So this is MB, MAVA prime plus MB VB prime. Just make sure that I did the MAVA prime plus MB VB prime is equal to MAVA plus MB VB. Yeah. So this is what we get. This is the relationship between velocities before and after the impact. Right? So if object A is moving with velocity VA and object B is moving with velocity VB before impact, after the impact, object A is going to have velocity VA prime and object B is going to have velocity VB prime. This is the total linear momentum of A and B. That's what it tells us. It says the total linear momentum of A and B is conserved. This expression here, what it's trying to communicate, it says the total linear momentum of A and B is conserved. Right? What was linear momentum? Remember, linear momentum was mv, right? That was the definition of linear momentum. So this is what this expression is telling me. It's telling me if I sum up the linear momentum after and a linear momentum before, it's the same. Right? Linear momentum after linear momentum before. And that's how I just wanted to show you that we have a conservation of linear momentum during the impact of two objects. All right. Now next we're going to look into possible outcomes, right? This is good. We know that we're going to have a conservation of linear momentum during the impact, but we want to know, as I said, we want to know more. We want to get the sense of dynamics of the system. So what we need to figure out is that what happens next, what happens after the impact, and what happens after the impact really depends on how do these two objects, what they are made of, for instance, right? This, as I said, we're just going to stick to the kind of kinematics or dynamics of the impact. We don't really go into the material science side of it and the whole energy discussion, but it really depends on what these objects are made of. What is we'll talk about the coefficient of restitution. What is that, and how much of energy is released because of this impact, and it really depends on those kind of things, and depending on what kind of material they're made of, what kind of impact we're dealing with, we're going to classify how to study the impact. Right? I'm just going to put them under possible outcomes. Right? It could be just after, when there is an impact, they might stick together and go together. After that, there might be an impact like two on a pool table, two balls, when they hit each other, after the impact, they just get separated. That's another outcome. There might be, the impact might be totally on the same line. Both objects can be moving on the same line, so they get, there is an impact and they just go back on the same line, or they get separated on the same line, or it can be with some angle. Right? Again, a good example would be on a pool table when two balls hit each other, depending on if it's a straight hit or it's a little bit of angled, right? And with another ball or with the table's edge. So we'll look into those and possible outcomes, and based on the type of outcome or what happens, we come up with some expression how to study the dynamics or the effect of impact on the dynamics of the motion.